Okay, thank you. Okay, so the first two lectures I'm going to talk about some general issues, some general aspects about topology in condensed matter. So it will be quite introductory, really introductory. I don't know how many people are really in condensed matter theory and how many are in other fields, but it will really be very basic level. And also feel free to interrupt and ask questions, because that always works better if people ask questions if they don't understand something. Okay, so this slide, you probably have seen it many times. What is topology? I mean, we are used with the idea that two objects are equivalent, for example, like a donut and a cup, because they only have one hole. So topologically, these two, even if they look different, they're equivalent, because you can continuously deform one shape into the other. If you had a sphere, for example, it would be not that would not be the same. It will not have the same topology, because you cannot deform a sphere continuously into a donut or a cup. But these two, even if they look different, they are topologically the same. So this is a very simple example from the day-to-day life. So nothing to do with condensed matter, but this is an example that is being used very often to describe the idea of topology. So two things which look different, but they can be deformed continuously to go from one to the other. Okay. In condensed matter, what does topology mean? So first of all, if we have two Hamiltonians that can be deformed smoothly into each other, then we can say that they are topologically invariant. So in practice, we have a Hamiltonian, and we have some parameters which are characterizing the Hamiltonian. And if some topological properties of this, if some properties of the system stay the same, even if we modify the parameters, we say that the system is topological. So, for example, we have a Hamiltonian which has some properties, some parameters, and the system described by this Hamiltonian exhibits edge states. That is the most typical example of topology in condensed matter. We have a Hamiltonian, and the corresponding system exhibits edge states. Now, if we modify the Hamiltonian a bit, if we change the parameters a bit, the system will still exhibit the same edge states. So we say that the system is topological because these edge states are stable. They are stable with respect to a modification of the parameters, and they are stable also with respect to other modifications of the system. For example, we can add disorder, we can modify the shape, we can introduce a lot of perturbations in the system, but the edge states remain stable. They are there no matter how much. Actually, it's not so general. You cannot perturb the system up to infinity. If you introduce a lot of disorder, then these edge states are destroyed. But up to some value, you can deform your system, and the edge states are still there. So what type of, like I said, what type of perturbations you can introduce that still preserve your edge state? In general, we can have disorder, we can have a lot of impurity potentials, for example, a lot of impurities in your system. We can also have a disorder in the shape. We have a shape which is neither square nor round nor any definite shape, but the edge states are preserved no matter the amount of impurities or the amount of disorder in the shape of the system. Like, for example, here also we can have some sort of defects, and also we can have some perturbations in the shape. And also, like I said, we can modify the parameters of the Hamiltonian and still preserve the edge states. And we are going to see in many examples that there is going to be some topological characteristic which stays the same for some range of parameters, and that at some point, when I change the parameters too much, I go through a topological phase transition, and these edge states are being destroyed. So like here I have some zero energy edge state, and then if I modify the magnetic field in this example, then for some critical value, they are being destroyed. But for a wide range of parameters, they are there, and they are stable. So that's what we call topological edge states. So I'm going to talk about topological edge states, but to make the to make the to distinguish from the non-topological edge states, I'm going to start with the non-topological edge states. To just give you an example, how do you form non-topological edge states first? So before starting to talk about Majoranas and other topological type of edge states, I'm going to first talk about non-topological edge states. And the simplest example you can think of which exhibits non-topological edge states is graphene. And then we're going to see what is the difference between topological systems and non-topological systems. So I mean, I kind of summarized things here, but I'm going to go on the board and I'm going to give you all the details of the graphene more, simply. I don't know if you are familiar with tight binding and how do we derive the Hamiltonian, for example, for graphene and for other tight binding systems. I assume that not everybody is familiar, so I'm going to really start with the very basics, and I'm going to tell you how do we arrive with this type of Hamiltonian and what does it mean. I mean, when we are talking about the tight binding model. You probably, those of you who took condensed matter courses, you probably know, but those of you who haven't, I mean, maybe it doesn't hurt to hear it again. Okay, so graphene is based on carbon atoms, of course. So I have a nucleus, and then I have electrons which go around the nucleus. Okay, so we know that the chemical structure of carbon is 6. I mean, it has 6 electrons. That's what we're interested in. And the orbitals, they are distributed in orbitals like that. I have 2 on the first s orbitals, 2 in the second s orbitals, and 2 in the p orbitals. So what are the orbitals? So you know that the s orbitals are kind of round, like spheres. So I have the first orbital which has 2 electrons, and this is sphere. Then I have the 2s orbital, and I have the 2p orbitals which look sort of like that. And I draw them like that, so they are aligned along the 3 directions of space. They look like some 8s. So then I have 4 electrons which have to go in the 2s, 2p orbitals. So how does it usually work? It doesn't work so simply. I don't get 2 orbitals in the 2s and then I get 2 orbitals in the 2p. What happens with carbon, which is a bit more tricky, you get what is called the hybridization. So the 2s and the 2p orbitals are going to hybridize. And there are 2 situations. One of them is what is called Sp3 hybridization. So the Sp3 hybridization, I'm hybridizing all these 4 orbitals, and I get 4 deformed orbitals. I don't know if I'm going to draw them very well. Something like that. Okay. I have 4 Sp3 orbitals, so I mixed up all these 4 orbitals together. So I form these 4 Sp3 orbitals, and I have 4 electrons. So each of them is going to go into one of the orbitals, and is going to bind with the other carbon atoms, and is going to form diamond. Diamond is very stable. So each of these electrons is going to bind, is going to make a covalent bond with another orbital from a different carbon atom, and I'm going to get this kind of, I don't remember exactly, not pyramidal, but whatever, 3D structure, which, tetrahedral, exactly, structure which corresponds to diamond. And that's very stable. I see I have no free electrons. All the electrons are bound, 1 electron from each. All the electrons of the carbon atoms are bound with neighboring atoms, so I have a tetrahedral structure, and that's very stable. And we know the diamond is one of the strongest material in the world, and this also comes from its chemical structure, which is very, very stable. But this is not the only type of hybridization that I can get with carbon. The second one in sp2, in which I'm only taking 1 s orbital and 2p orbitals. So I have an s, well, I'm not going to draw the s and the p again, and I'm going to form the sp2 orbitals, which look like, it's also some sort of 8s, I think. Well, but I have only 3 of them, and they are planar. They are going to live in a plane. Okay, and they are going to be kind of at 120 degrees between each other. These are the sp2 orbitals. And each of them is going to get one electron. But you see, I'm going to be left with one p orbital, a free p orbital. And this p orbital is going to go perpendicular to the plane of the sp2 orbital. And in the plane, the carbon atoms are going to bind the same way as in the diamond. They are going to bind with neighboring atoms, and they are going to form a hexagonal lattice, which I have this 120 degrees between the orbitals. So I'm going to form, in the plane, I'm going to form a hexagonal lattice. So I'm going to have my orbitals like that. And the last p orbital is going to be free. And I'm going to have one electron in it. But I see that this orbital is not bound to anything. So the planar structure is the graphite structure. They're forming the planar graphene structures. But I see that on each atom I have one free electron. So this free electron, what can it do then? It can move. It can move from atom to atom. It can hop. What we say in condensed matter, it can hop. Because there is some superposition between, there can be some superposition between this free p orbital on this atom and on this atom. There is some overlap. And this allows the electron to hop between two neighboring atoms. And this hopping we call is the basis of what we call the tight binding model. So the tight binding model is basically a model in which we have an electron which sits on one atom, and then this electron can move between the atoms on the lattice. So in carbon, in graphene, that's the way things are being formed. It's coming from the chemistry. I have these sp2 orbitals which are forming the planar structure, and then I have one p electron which is free and can hop between two neighboring atoms. And that's the basis of the tight binding model. So that's what I wrote on the first line there. The A's are operators which correspond to creating an electron on an A type of site. We see that the hexagonal lattice of graphene has kind of like two sublattices because I have two atoms per unit cell. It's not like a simple rectangular square lattice, but I have two atoms per unit cell. So the A's denote the operators which create electrons on the A sublattice, and the B create electrons on the B sublattice. And this term in second quantization is the hopping term, which is telling me that I can hop an electron from one A atom to one B atom. And to first approximation, we are not going to bother about hopping electrons from between two red atoms. We consider this is too far. There are some models in which we also take this into account. But to first approximation, we are only going to consider that electrons can hop only between two neighboring sites. So only between A's and B's. And this is going to give me this type of hopping Hamiltonian, which you see in the second quantization. It's telling me exactly that. And we say that this gives you the kinetic energy of the Hamiltonian. So this is like the kinetic term, so because it describes the dynamics of the electron. And I'm going to first give you a simple example how do we arrive from a tight binding Hamiltonian to a k-squared, for example, dispersion, to see why these hopping Hamiltonians actually correspond to the kinetic term. So, okay. Assume I have first a 1D. I have a 1D structure. Okay, so the I's are the lattice sites. And I also have the same type of hopping Hamiltonian. So I'm going to say that H. We're going to use this notation in which means that the hopping is possible between nearest neighbors. So this kind of brackets mean nearest neighbor type of processes. So I'm going to say T is like some sort of constant, which corresponds to the amplitude of the hopping, and it's proportional in general to the overlap of two orbitals sitting on two neighboring atoms. Okay. On the 1D lattice, J has to be I+1 because that's the I'm going to go back to I then. T, C, I, dagger, C, I plus 1. And, okay, let's do this then. Okay. We are going to do a Fourier transform of these operators from the real space to momentum space. And we are going to write Ci. This is a normalization constant, which is proportional to the size of the system, roughly, square root. And well, actually, I'm going to go directly to the continuous version. We can do it like that, but we can do it. Okay. I'm going to integrate over k. I can sum over k discrete points, but I can also do a continuous version of the Fourier transform. And I'm going between minus pi over a and pi over a. This is the Brillouin zone for one-dimensional systems. Okay. These are all the allowed values of k in the periodic description of the Brillouin zone. So then I get ck dagger. Ri is the position corresponding to the I atom. So now if I introduce that in there, I get that H is minus T sum over I. Then I have an integral ck1. I'm skipping the okay. I have ck1 dagger k1 then I have ck2 k2. Now I have Ri plus A, since my second operator is acting on the neighboring side. And if I do now the sum over I see that I have here these two terms. So I can do the sum and I get a delta function. This is non-zero only if k1 equal to k2. Sorry. Okay. And summing over I is going to give me some size of the system normalization constant, but then if I go between discrete and continuous convention, then the n times this Dirac is going to be 2 pi delta k1 minus k2. And this delta, I can use it to get rid of one of the integrals. So I'm going to be left with, okay, and then I get ck dagger ck, and then I'm going to get minus I ka. And I forgot to say that here we always to have this thing Hermitian, we always have the Hermitian conjugate. So I get always the Hermitian conjugate term. This is going to give me a 2 cosine of ka. So this is going to be minus t cosine of ka, sorry, integral of dk of the pi. Okay. So we see that I'm in momentum space. I have a Hamiltonian, and I have some sort of energy. So this is the energy of my electrons. And if I make an expansion close to the minimum of this term, so, okay, where should I draw it? Let's see that. Well, maybe I shouldn't do it here. Nice place. Do it here. I have a minus 2t for k equals 0. And I have a 2t. So that's the band structure for my Hamiltonian. So if I'm going to make an expansion close to k equals 0, this is going to become minus 2t. Sorry? Ah. So this is going to be so you see that I have constant term, but I also have this, because I'm starting with the level of minus 2t, but then I have a k squared term, k squared a squared term, and this is going to be basically the kinetic energy of my electrons in this tight binding model, and you can kind of see it here, because then here things are more or less parabolic. So then the dispersion of my electrons close to the bottom of the band is parabolic. So this is telling me that the tight binding model corresponds to some kinetic energy. This gives me the kinetic energy of electrons moving in a lattice. And we go back to the classical quadratic dispersion of electrons if we stay at energies which are close to the bottom of the band. So this is, just very simple. How do we go from a lattice in which we have hopping electrons and a quadratic dispersion describing the kinetic energy of my electrons? Okay. So in graphene things are a bit more complicated, you see, because I have a hexagonal structure. So in 1D or even in a 2D square lattice, it's very simple. I make this type of expansions. I have the hopping, and I get cosine of k a, which can also be cosine of kx a plus cosine of ky a if I'm going to have a square lattice. But in graphene things are a bit more complicated, because you see these Fourier transforms which I introduced here are not going to give me some very simple factors, but are going to give me this e to the ik delta 1, e to the ik delta 2, and e to the ik delta 3 times of terms. So for graphene, when I repeat this exercise, very simple, it's exactly the same procedure. I'm writing the Fourier transform. I'm for the real space operators into momentum space. I'm going to get a Hamiltonian which in these spaces, the basis of the A and the B, is going to have this form. It's 0 delta k 0. Delta k is this kinetic term, and it's off diagonal because I have only terms which go between sides A and sides B. I don't have an on-side term. In any case, we may have the chemical potential, but it's not. I didn't put it in the hopping Hamiltonian. So I have these off-diagonal terms which corresponds to moving between electrons on sides A and electrons on sides B. And it has this term because, as I said, when I take the Fourier transform, all these factors are going to interfere, the same as e to the ik is coming in here. Here I'm going to have e to the ik delta 1, e to the ik delta 2, and e to the ik delta 3 type of terms. And if I put in the numbers, if I put delta 1 exactly what it is, it has a in this direction and 0 in the other, and delta 2 and delta 3 have corresponding values to the 60 degrees angle, I'm going to get and I'm going to diagonalize this Hamiltonian to get the band structure. I'm going to get these values for the band structure. Well, you cannot get much after this formula. It has kx and ky in it, of course. So it's going to, it has some specific form, but we are going to look at it more, more graphically. So if I plot it here, if I plot this dispersion as a function of kx and ky, it looks like that. I see that E as a function of kx and ky has this kind of bizarre type of shape, like a dome. And the two bands, I call them two bands, but anyway, the energy dispersion goes to 0 at 6 points, which are the corners of the Brillouin zone. So this is what we are calling the Dirac points. So these are the points in which the energy goes to 0. And if we look at the dispersion of the electrons close to these points, it's linear. So if we make an expansion of E close to these 6 points, we are going to see that the expansion gives us some linear form. And I have something like cones. So I have some cones of low energy. I have cones of the cones of dispersing cones. If I take like a more top-down view, I see that I can also depict it a bit differently, and these are like the equal energy contours. If I take cuts like that, so these are my 0 energy points, and then close to some energies, and I have these contours, and then these contours are changing kind of topology, and they merge, and they form these triangles, and then I have circles corresponding to these areas. So this is like a view of the graphene graphene band structure. Okay, so why now has graphene exhibits edge states? And what type of edge states can graphene have? So this is like some picture from some measurements of some theoretical predictions, and we see that we can see some high intensity in the local density of states close to the edges of graphene. So usually that's how edge states are being observed or predicted, by measuring or calculating the local density of states close to the edge, and we see that we have some high intensity which is localized close to the edge. You probably know what the local density of states. I mean, the simplest description is the absolute value of psi squared. So if I have a wave function, which is an eigenstate of my Hamiltonian, if I take psi squared, this is going to give me a local density of states. And for now, it's a rough idea, but then next lecture, I'm going to give you a bit more details about the exact definition with respect to the eigenstates of a Hamiltonian. So the local density of state, which is the psi squared, the eigenvalue squared, has some high intensity close to the edges. But graphene, as I said, is non-topological. The edge states which form depend on the structure which I have on the edge, depend on the lattice structure which I have on the edge. And graphene, if I cut it one way or the other, I can have different types of edges. I can have armchair edges. They kind of look like armchair. You imagine sitting here, and these are like the arms of the armchair. So this is an armchair edge, and this is a zigzag edge. And the two are not equivalent. Again, this is not a topological system. The two are not equivalent. We can have edge states actually forming on the zigzag type of edges, but not on the armchair type of edges. Okay. Okay. And how can we understand the formation of these edges? In the next lecture, I'm going to give you more technical details about how these calculations are being made. We are called like tight binding numerical calculations, but for now, I'm going to just give you an idea. So again, this is the band structure of graphene. And imagine I have a ribbon. Okay, I have a finite size system which has two edges, one on the right and one on the left. Imagine this one and this one. Okay, so I have a finite size in this direction. If I have a finite size in this direction, I have no more translational invariance in this direction, only in this direction. Along this direction, what I have is a quantization of the momenta. So not all the momenta along this direction are allowed, because I have, the usual particle in the box problem. And then if I look at the bulk band structure, to get the ribbon band structure, what I need to do is basically to cut along some lines which correspond to allowed values of k along this direction. So I'm imagining I'm looking along, this is ky, this is y, this is ky, and only these values of ky are allowed. So I imagine that I have to cut my big band structure in 3D by some planes which are passing through these lines corresponding to the allowed values of ky. So imagine that I'm projecting these planes over this 3D structure, and this is going to give me cuts. Okay, so now if I'm taking a look like that, I'm going to superpose all the possible cuts of allowed values of the dispersion, and I see, for example, the cut which corresponds to ky along this line, which is basically here. You see, I'm going to have this line. Okay, okay, and this line is this line here. Okay, so this is this value of ky. If I take a value of ky equals 0, so here the cut corresponds to, let's say I have a peak here, and I have a 0 value here, and it's going to be this one. Okay, it's going to be this. It's going to be this, which goes to 0 here. So it's going to be this line. Okay, and in between, I'm going to have all the allowed values of ky giving lines of allowed dispersion. So I'm just cutting again. I'm cutting this 3D dispersion. I'm going to make discrete allowed 1D dispersions. I'm going to superpose all of them, and this is going to give me the dispersion of the nanoribbon. So again, this is this thing which has a peak here. This is this one which has this peak here, and then I get, all the other things in between. So these are the black lines, but I also have this blue line. If you look at this blue line doesn't come from any cut from the 3D band structure. So I have all these bulk bands which are coming from discretizing the 3D band structure, but I also have a blue line, which you can see there is no equivalent in the bulk. So this corresponds to the edge states. So this is going to be exactly my new thing which appears when I have a ribbon. So this blue state is the edge state. And it is bizarre because it has an interval in which it gives me a flat band at 0 energy. So I have an edge state which has actually 0 energy and which exists between two specific values of kx. And this is the edge state. I mean, and this type of calculations, I cannot. Unfortunately, I mean, for now, I don't have a simple way of telling you how it's being obtained. I'm going to explain you next time. This type of predictions are made using tight binding, numerical calculations. We can call them exact diagonalization type of calculation, but not in the sense of exact diagonalization in the strongly interacting system, but I'm going to explain that next time and what type of technique we use to obtain this type of things. I'm just taking my 2D lattice and I'm going to diagonalize it using some numerical code, and this is going to spit out this type of picture. And I'm going to see that besides what I could infer myself from the bulk band structure, I'm going to get this extra mode, which corresponds to states which are localized on the edges. If I look here and I plot the wave function which corresponds to this point in real space, I'm going to see that this is localized on the edges of my system. So this is that's why we call it edge states, because it's localized on the edges of the ribbon. Okay. So again, this is the graphene. This is the graphene case, non-topological edge states, and they are destroyed by disorder, and they depend on the type of edge, the lattice structure of the edge. They are not stable with respect neither to disorder nor with the structure of the edge. Okay, again, this is the same thing with what I said. This is the bulk, this is the edge, and then the flat band is the edge states. Okay, so now I'm going to go towards what we are discussing in this course, which is like topological edge states. And in particular, I'm going to spend a lot of time discussing Majorana states. Before getting into some concrete example of a model which exhibits Majorana states, I'm going to give you some very basic notions about what a Majorana is. So Majorana states are condensed matter version of Majorana fermions. Coming from other fields, you may know what a Majorana fermion is. They are particles which are own antiparticles, like supposedly neutrinos. But in condensed matter, I mean, it's a bit hard to realize this condition. So what we can do to have a self-adjoint particle is to make a combination of electron and a hole. So electron and holes are excitations of the Fermi sea. We know I have a sea of electrons. If I make an excitation, I add a particle above the Fermi sea, and I also add a hole in the Fermi sea. That's an electron-hole pair. And I see that this is a Majorana in the sense if I take the adjoint of this combination, the electron becomes a hole, the hole becomes an electron, and this is self-adjoint. So this is a Majorana state. In condensed matter, a combination of the electron and the hole is a Majorana state. However, if the Majorana fermions in particle physics have fermionic statistics, because they are purely fermionic excitations, Majorana states in condensed matter have non-abelian statistics, which is a bit bizarre. I'm not going to get too much into that, but you can, for your own general, culture, is good to know that the states in condensed matter, the Majorana states, they don't have fermionic statistics, but they have non-abelian statistics. Meaning if I exchange them, they just don't change phase like fermions, but they get a very complicated mess of their wave function. So that's non-abelian statistics in 2 words. And these states are topological, meaning that like opposite to graphene, their formation is not going to depend on the details of the system, the type of the edge, and disorder, and because of that they are protected. So if I add a bit of the disorder, they are going to still be there. And you can imagine this is very exciting for people who do quantum computation, because they say, oh, I'm going to make stable qubits for quantum computation. They're not going to be influenced by disorder, by the details of the system. I'm going to use them for quantum computers. Especially, they also have this nonabelian statistics, which is quite important for them. Well, life is not so simple as that. That's the theory. I don't know if they're really going to be used for quantum computation, but the idea is that, in theory, they are good candidates to be used for quantum computation. And there are some materials that are proposed to host Majorana states, but for now, the experiments which have been performed, for example, transport, in which zero energy peaks have been observed in wires, or STM, in which, again, zero energy peaks have been observed close to the ends of some magnetic chains deposited on like some substrate. There are still contradictions. There are still controversies in the literature. People say, well, they can be Majorana. Other people say maybe they are not Majorana because there are other things. So for now, there is no consensus in the community saying we have observed Majoranas. We are still debating. Some people say yes, we did. Some people say no, it's not really that. It could be something else. So the idea is that most people believe that the observation is still controversial, and we still need more experiments to test.
You would say that for both?
Yes. Mm-hmm. Okay. So now I'm going to go back to the board, and this is a more complicated example. I'm going to give you first the simplest example, which exhibits Majorana, which is a Kitaev model. Well, when you hear Kitaev, you're going to say, oh, Kitaev, I know this. But it's not the same Kitaev model that people in high energy are using. I mean, this is a different Kitaev, which Kitaev, I think, has same Kitaev, but not the same model. I think this Kitaev guy is very prolific. He has many models on his name. So this is a very simple model. It's not a complicated Kitaev model that you are more used to it in other fields. Okay, I'm going to start on this one. Okay. Okay. Before giving you the form of the Kitaev model, I'm going to say a few more words about Majorana. So, like I told you before, we use this second quantization in which C dagger creates an electron and C creates a hole, or alternatively, it annihilates an electron. So, if you look at these operators and say, well, how can I make a Majorana out of these things? And I told you before, Majorana in condensed matter are this type of electron-hole combinations. Then I'm thinking, okay, if I would have this type of excitation, like this C dagger plus C, so a combination of electron and hole, this should be a Majorana. This should be self-adjoint. And indeed, if I take the Hermitian conjugate of this thing, I get the same thing. So this is this combination, a combination of electron and the hole, or alternatively, a combination of a creation and an annihilation operator. This is a Majorana. And we are going to write C dagger and C, a superposition of a real part and an imaginary part, so like a superposition of two real operators, which are the Majorana. So I'm going to write C dagger as superposition of gamma 1 plus I gamma 2, and C as a combination of gamma 1 minus I gamma 2. And if I go back, I'm going to see that gamma 1 and gamma 2 and indeed, these two, if I take, like I said here, if I take the joint, the Hermitian of these two, I'm going to get the same thing. So these are going to be my Majorana states. So I wrote the electrons, so the elementary excitations of my condensed matter basis for whatever I do, a superposition of two Majorana operators. So mathematically, it's not too It's mathematically it's not too complicated, but physically it's a bit more complicated because I can do this, you know, on the board, but to get a system which actually does this and actually gets excitations that have free excitations that are gamma 1 and gamma 2 is much more complicated. So mathematically I can always decompose my electrons into Majoranas, but physically to get a system which does this and shows the gamma 1 and gamma 2 excitations is much harder. So before I get I might. I haven't. Maybe. I think I either do this, I think, on both of them, or I have one of them has. Well, if I do this, I think it's okay. I think I have too many on halves indeed. C dagger plus C. If I don't have the 2, if I leave a 2, then I get. Gamma 1 is just a sum without the 2. Yeah. Okay. So one subtlety which I will talk about it here is that you see I have a combination like this, but people don't talk about it too much. But well, I want to mention it is that I can always have. Okay, I'll ignore the normalization constant. So I'm going to write an operator gamma, which is going to be theta. Okay. So I can get also a combination which has a relative phase between the electron and the hole, and also has a relative, has an overall phase. So this type of operator, if you look carefully, this is also, it could be a Majorana. If you look at that, theta, this is C. Okay, up to some phase factor. So this is going to be, I think, 2I theta into the minus 5. Okay. So this is the same. So gamma dagger is the same as gamma up to some phase factor. So what do you think? Is this a Majorana or not? It actually is a Majorana. But the actual definition of Majorana being self-adjoint is not fully accurate. There is also a phase factor here that can appear. So the most general Majorana form is not just C dagger plus C, but it can have these two phases, a relative one and an overall one, which is going to appear here. So gamma doesn't have to be equal to gamma. It can be equal to gamma up to phase. So this is usually not being said, but if you look at all everybody does, even this one, if you take a gamma dagger, is going to be minus gamma, even this one. So there is always this phase which is not being mentioned. But the Majoranas, they are not really self-adjoint, they are self-adjoint up to phase. I'm going to, if I have time next lecture, I'm going to tell you why this is important. I mean physically, in some physical examples, how these phases are intervening, which is quite interesting. Okay, so now let's go to the Kitaev thing. Okay. So Mr. Kitaev came up with this idea. So how can I get free excitations which are gamma? So if I think of a regular Hamiltonian, I can think about it like that. I have on the side I have an electron, which is superposition of gamma 1 and gamma 2. And it's the same for all sides. Okay. And normally, for regular condensed matter systems, these two are paired together. And I don't see the gamma 1 and gamma 2 together. I only see the C dagger. Or the C, whatever, C dagger or C. So I only see that. How can I make free excitations out of this chain? How can I unpair these two gammas sitting on the same side? So he said, oh, I need to build a Hamiltonian which is pairing this with that. Okay? I'm pairing, instead of pairing the gammas on the same side, I'm pairing gammas on neighboring sides. Okay? I'm going to make some sort of pairing between Majoranas on neighboring sites. So I can write the Hamiltonian. And I'm going to get it. Okay. Which is going to be gamma 2 to I. Okay. So I'm pairing the one gamma sitting on site I and with one gamma sitting on the neighboring site. So I think the way it's being numbered is this is gamma 1, gamma 2, this is gamma 3, gamma 4, blah, blah, blah. So gamma 2i, gamma 2i plus 1 is a gamma sitting on site I, this, which is the second one, is paired with a gamma sitting on the site 2i plus 1, which has 2i is here, yeah, we're sitting on the site 2i plus 1, but the first one sitting on 2i plus 1. So I'm pairing neighboring gammas on different sites. So this, if I'm solving this Hamiltonian, it's a simple Hamiltonian. I mean, it's just it's not. It's the same as the tie binding thing. It's like it's just that gammas don't have daggers, but it's the same type of Hamiltonians. I'm going to see that this Hamiltonian, since it's pairing neighboring gammas, is going to leave these sites free. So this is a bit. I'm going to get into the details of the actually solving the Hamiltonian, but for now I'm just kind of giving an intuitive picture. So when I'm writing down this type of pairing, I'm going to get a free excitation, which is gamma on this side, and I have a free excitation, which is gamma on the other end of the system. So on the two ends of the system, I'm going to have free gammas. I'm going to have free Majorana states, because all the middle things are going to pair, and I'm going to left this one unpaired and the other one unpaired, and I'm going to get like two Majorana states on the two end sides of the system. So, but this is written in the gamma language, in the Majorana language, I mean, to get an idea. But of course, given these relations, I can go back to the electron type of language, and I'm going to write the Hamiltonian, which corresponds to this type of pairing, and is going to be okay. So this is what's called type. It's equivalent of this. But now see, I wrote it in the fermionic language. So I have three terms. I have the chemical potential, so I can change the chemical potential of my system, which is proportional to the density of the electrons on each side. I have the hopping term, which I described in great details before. So I have the hopping of electrons between two sides, and I have an extra term, which, if you see, it's a superconducting term, because it's pairing two holes or two electrons. Oh, I forgot the Hamiltonian conjugate, of course. So if you plug in this value, if you plug in this type of formulas for the C's, you are going to see that if T equals delta, then these two are identical. I'm going to go between this and that. I mean, I can do the exercise on the board if you want, but it's pretty straightforward. You just put in gamma dagger. You can put C dagger as gamma 1 plus I gamma 2 here, and you can cancel all the middle terms, and you're going to see that this is giving you that. It's going to pair. It's going to pair neighboring gammas, like in this form. Okay, but this is a physical Hamiltonian. I mean, this is more like a mathematical tool that I'm trying to see how to form Majorana, but this is a physical Hamiltonian. It has a superconductivity in it. It has a chemical potential, and it has a hopping term. So this is something which we can imagine. Can this exist in nature? Because it has, physical ingredients in it. This one doesn't, but this one has physical ingredients. It has, whatever we find in everyday experiment, in everyday life, condensed matter, scientist activity has all the simple ingredients which we can put together and see eventually get a Majorana. Okay, so now let's work a bit with this, more with this model, and try to understand why this exhibits Majorana. Okay. Let's try to give you some. Okay, like that. So this is like an intuitive, very simple intuitive way, but let's try to do some sort of a different approach, just staying in the fermionic language, don't go into Majorana language, just look at this Hamiltonian in this form. So one thing condensed matter theorists do when they see a Hamiltonian like that, they solve it using, like I said, tight binding. Like they just do the chain, and they do an exact diagonalization. See, okay, let's look at the solutions of these Hamiltonians. Let's look at the eigenstates. What are the eigenstates of this Hamiltonian? It's a lattice Hamiltonian, so let's look at the lattice Hamiltonian. Let's look at the solutions of the lattice Hamiltonian. And again, I'm going to talk a bit more about the actual technique next time. But so if I do a I look at the real space wave functions of this thing, and I plot, I'm taking delta equal t. So I said that in this case, these two Hamiltonians should be equivalent, and then I'm varying mu. Mu is going to be a free parameter in this thing, and I'm looking at first at the spectrum of this Hamiltonian. Okay. I'm plotting the energy of the spectrum, the energy spectrum of the Hamiltonian as a function of mu. I'm going to see that for mu between minus 2t and 2t is going to have some zero energy. It's going to exhibit some zero energy state, and it's going to exhibit some other bands. Something like that. And the same thing for the negative. Okay. But the important thing is between minus 2t and 2t, I'm going to have a zero energy state forming, which is the solution of this Hamiltonian. And if I plot the local density of state, or the psi squared, at values of mu in this interval, as a function of position, so this is the first side and this is the last side of my system. I'm going to see that this psi squared for mu between minus 2t and 2t is going to have kind of like this type of structure. I'm going to have high intensity close to the ends of the wire. I'm going to have states which are localized on the ends. Here, I mean, I'm not talking about edge states since this is a 1D system. I'm going to talk about ends, basically end states. So I see that for the mu between minus 2t and 2t, I'm going to have end states. Okay. Then if I'm varying mu close to 2t, I'm going to see these states are actually kind of penetrating more and more into the bulk. And for mu bigger than 2t, they are going to be like that. They are going to become bulk states. So if I look at the state here, this is going to be a state which is localized in the bulk and not on the end of the system. If I look here, then this state is going to be localized basically on the ends of the wire. So it's going to be, I still haven't shown you this is a Majorana. I'm saying you for now, the first thing to do is to see what eigenstates I have and where are they localized. So if I do this analysis simply numerically, I'm going to see that for this interval of mu's, the states are localized on the ends and they are zero energy. So this is what I found till now. Okay. Yeah.
Are you talking about the ground state?
Yes, I'm talking about the lowest energy state. I'm talking about this state. Yes, the one that is at lowest energy. So I'm following this one basically like that. Yes.
And at the point near equals to t,
The system becomes gapless at mu equal to t. Yes. Mm-hmm. Yes. So you see the bands are touching here, and the system is more or less gapless. The gap is closing at mu equal to t. Mm-hmm. Yes. Okay. so this is the spectrum. So why is this a Majorana? I'm going to actually give you the details. Also in the next lecture, I'm going to actually derive the wave function with various methods. I'm going to derive the wave functions for this Hamiltonian using tight binding and then using matching and a few other techniques. So next week, the lecture of next week is going to be based more on methods. But just in 2 words, if I'm looking at when I do my tight binding, I can get my eigenstates, but I can also get my eigenfunctions. So the eigenfunctions I'm going to see, they are going to be superposition of electrons and holes. Exact superposition, I mean, you can think about it like that. So if I diagonalize the system, I'm going to see that the eigenstates which correspond to these values of mu are actually equal superposition of electrons and holes, and they are Majorana. And I'm going to talk much more about that later. I'm not going to prove it to you now. For now, the only thing I'm proving is that I have zero energy states, and the zero energy states are localized on the ends of the wire. So the Kitaev model is exhibiting zero energy states which are localized on the ends for this interval. Okay. So now let's talk also a bit about not only the spectrum, but also let's go into the momentum space for this model and see exactly like what he was asking, how is the band, if the system is gapped, or if it has a gap or it doesn't have a gap, and where is this gap closing. We're going to make connections with type of bulk arguments later, so this is going to be useful to understand also the band structure in K space to see if the system is gapped or not. And should I go into that now? I mean, okay, it will take yeah, I can, it shouldn't take too long. So, okay, so now go into momentum space. So like I showed you before, for the simple chain, we can do the same type of transformation. I do a Fourier transformation. Okay, dagger. Okay, I'm doing the same type of Fourier transform, and maybe I shouldn't really spell out all the steps of, how do I implement all the topping terms and everything. I can give you the result because it's very straightforward. It's exactly like for the chain, but a bit more complicated because it has some extra terms. Okay. So you recognize the hopping term. I mean, it's the same as before. It's the hopping term for the chain. Then I have the chemical potential, which doesn't have any K dependence because there was no, there are the two operators which were appearing here were on the same side, so there was no K term left when I take the Fourier transform. So this is the classical hopping term which I derived before. The mu has no cosine of Ka because it's an on-site term. It doesn't have any K dependence. And then and then I have the delta term. Okay, that's the term which came from taking the Fourier transform of the Ci dagger Ci plus 1 term, because it's this term. Sorry, I have to write the term also. Now, of course, I have to pair terms with opposite K because for momentum conservation, when I'm pairing, when I'm doing the Fourier transform, I'm going to get constrained that I'm pairing electrons with opposite momentum because they are like, otherwise I'll have no conservation of momentum. Okay, so this is, how should I say? This is like the Hamiltonian which I get simply by doing the Fourier transform, but what people do to write this in a more interesting way is to to use what we call the Bogoliubov-Dijen formalism, and we're going to write now this in a matrix, in a 2 by 2 matrix form, which has on one line the electrons, on the other type the holes. This is going to put more into, is going to make more clear the electron hole type of correlations which appear into this Hamiltonian. For now, I have it like that, but people like to do it in to write it in this Bogoliubov-Dijen type of form, which is going to be a 2 by 2 matrix and is going to kind of make more obvious this electron and hole components of this Hamiltonian. So I'm going to do it here. And it's going to be easy to get the band structure once I put it in the BDG form. Okay, so let's do Bogoliubov-Dijen. It stands from there. So I can, in a way, I'm doubling this Hamiltonian. So I take 2 copies of this Hamiltonian, one for the electron and one for the hole. So I'm kind of, write the double of the Hamiltonian. So it's in some sort, it's like taking a 2H. Well, you can think about it like that. So what I'm going to do, I'm going to say that instead of having CK dagger CK, I'm going to write CK dagger CK plus and actually this can be written as minus C minus K. We know that fermionic operators commute, so I'm going to write this, which is basically just double of that, because I'm just integrating over OK, so it doesn't matter if I see K or C minus K. So I double this, and then I'm changing the order of my electron in the hole, of the electron of creating and annihilating operator. So I'm writing this now as that. Okay, so if you look there, then this means that I can write my Hamiltonian in this basis. I'm going to define a basis, which is that. Okay, and I'll have a matrix H, and then I have CK, okay. So I have C. I'm writing now. I'm trying to write that into this basis. So this basis is the electron with momentum K and the hole with momentum minus K. So I'm just trying to now to reformulate my Hamiltonian so that it fits into a 2 by 2 matrix, which basically is going to be psi dagger, some H psi, where psi dagger is going to be this. Okay, so I double basically the number of degrees of freedom in my Hamiltonian, sort of. So you see that this term, the term which corresponds to the T and the mu, is going to appear off diagonally here, is going to appear. So this is on the first element here, I'm going to get CK dagger CK, and here in this corner I'm going to get C minus K dagger. The coefficients of the term of CK dagger CK should appear here, and the coefficient of C minus K dagger is going to be here. So then my H is going to be 2 minus 2T cosine Ka minus mu here, and then here I have to have a minus, because you see I have this minus term, so this I'm going to get minus 2T cosine Ka minus mu. This is going to be the term corresponding to CK dagger CK, and then the term corresponding to delta, look here, I have the CK C minus K, and this is going to be a term appearing here, because it's appearing here, sorry. I have a C minus K CK appearing here, the term here, and the CK dagger C minus K dagger is going to appear here in this corner. So the term, then I'm going to have CK C minus K, but it's the other way around, so here I'm going to have a minus 2 delta I sine of Ka, and here I have a 2I delta sine of Ka. So this is going to be my H. Okay. So I rewrote, everything I had there in this new basis, psi, And the matrix Hamiltonian corresponding to this is looking like that. So again, I have a minus because the first term is written as this minus that. So these two have to have opposite sign. And here I have these two terms, which if you look, here I have ck, c minus k dagger here with a plus, but here I have c minus k, ck appearing here, so I have to exchange them once. So this gives me a minus sign here in this lower corner. And here I have a plus because I have directly ck dagger, c minus k dagger from there. So that's the matrix Hamiltonian in the Bogoliubov division. In the Bogoliubov division form. So okay, just aesthetically, people prefer to write it a bit more compactly. It's nothing fundamental. It's like now I have it in this form, but you know, people like to use Pauli matrices. So I'm going. Then they write H is integral over K. Then they have the psi K dagger, and then H psi K with H being the first term is going to be minus 2t cosine Ka minus mu sigma z. That's because it's 1 and minus 1. And then they write that 2 delta sine fky sigma y. Okay. They write it in Pauli matrices language because it's simpler. Okay. And that's the shortened version of it. So now I can much easier get the band structure because you know I have it nicely in this form. And how do I get the band structure for a 2x2 Hamiltonian? I get the eigenvalues of the 2x2 matrix. So I'm going to get A or something. I'm going to put H1. Okay. So this is the form for the eigenvalues of my Hamiltonian. So the last thing I'm going to tell you before the break is how does it look if I do a plot. So I told you that I don't have the drawing anymore. I have like a end states for mu going between minus 2t and 2t. So it means these two values are peculiar. And indeed, if I'm looking at mu equals minus 2t, then the band structure is going to look like that. Let's put here minus pi and pi over a and pi. Okay. So I have a gapless thing at mu equals minus 2. T, this is going to be gapless. If I increase mu a little bit above mu equals minus 2a, then the system is becoming gapped. So I'm giving you an example here. Okay. Okay. I'm not drawing the lower band just not to make it too heavy. So this is going to be mu equals minus t. Okay. You see that it's becoming gapped both at k equals 0 and at k equals pi and minus pi. So it's gapped. Then if mu equals 0, actually it really looks straight. It doesn't depend at all. The band structure doesn't depend at all on k. If I now go to positive values of mu, then I get this. It starts closing here at pi and minus pi instead of 0. And the ultimate thing is for mu equals 2t. This is for mu equal t. And for mu equal 2t, I have this. Sorry. Okay. So now I get a gapless thing, but the gap is closing at pi and minus pi. Instead of closing at 0, now the gap is closing at pi and minus pi for mu equal 2t. So I have gap closing at 0 for mu equal minus 2t. Then I have a gap system, which becomes again gapless at mu equal 2t, but the point of closing the gap is different between minus 2t and 2t. At minus 2t, it is at k equals 0. and the 2t is at k equals pi and minus pi. So I have a system which on the whole interval between minus 2t and 2t is gapped, and is becoming gapless to these special points. And I'm not going to talk too much about it, but this closing of the gap points are actually the points of topological transition. So I have a topological gap between minus 2t and 2t, and my topological states are protected by this gap. And I have a non-topological gap outside of this interval for mu is larger than 2t and smaller than minus 2t, and there I don't have any topological states. And I see that if you go back to the spectrum which I draw, you've seen that the zero energy states, they're inside the gap between minus 2t and 2t, and then outside of that spectrum there was no topological state, and it was a trivial state. And inside this interval there was a gap, and there are the zero energy states which are being protected by this gap from the bulk state. So I mean, it's important to also have the band structure in momentum space to be able to make a connection to the real space understanding, and this closing of the gap is important to understand the structure of the topological system and where you have a band topological transition. And in general, I mean not in general, and the transition, the topological transition is associated to closing the gap. So there are these points of closing the gap for the yes.
So if t is not equal to delta, then you.
If t equal to delta. If t not equal to delta, the things vary a bit, but I think that for Kitaev model in particular, the same boundaries you have, minus t and 2t. That it's not, it doesn't change. But you have other models in which, when you vary one parameter, indeed the boundaries of topological phases are changing with each parameter. But this is quite a stable thing. I mean, you kind of have lines that's minus 2t and 2t, no matter the, you know. Okay, so I think for now that's I can stop now for the break, and then we can continue like in some, I don't know, five minutes or so.
And then we'll come
Okay.
Yeah.
Okay, so again, I forgot to mention, and somebody asked, and I'm glad. So this, when I'm talking about the K-space structure, I'm talking about an infinite system. Okay. So the infinite system, you see, I'm plotting here as a function of k. So in order to have a k, I need to have spatial invariance. So I need an infinite system without any boundaries. So when I'm talking about this band structure, this corresponds to an infinite system. This doesn't have any boundaries. So again, my system is gapless for mu equal minus 2t and 2t, with the gap closing at the minus pi over a and 0, and the system is gapped for the interval in between. But I'm talking, this corresponds again to an infinite system because I have translational invariance, and I can define band structure. I can define E of k. The moment I'm adding boundaries, my k is no longer a good quantum number because, you know, again, I have boundaries, I have quantification, so it doesn't work. So then, when I have a finite system, I cannot plot this type of thing. The only thing I can plot is what I'd drawn before, are all the values of allowed energies at a given value of mu. I don't have any more a k dispersion. I only have allowed values of energies. You can think about it, you know, in terms of quantification of ky, of k in these situations. K has only allowed values, and there are corresponding energies. So I have a spectrum. So this whole thing, this whole band structure, which corresponds to one value of mu, is projected basically. So mu equals 0, for example. Here is projected on some, you know, points. Here I only draw. Actually, I only draw the first band, but I have. No, sorry, no. Here it's good. But then when I'm doing the quantification, of course, I get multiple values of ky. So I have a discretization, the same way I had when I showed you the graphene 2D thing. Then when I was taking the quantification, then I was getting multiple bands because of the all allowed values of k. So now this band structure is being projected at one value of mu. So okay, mu equals 0 maybe is not a good idea. Let's take mu equal 2t. Okay, mu equal 2t is the white one. So now, when mu equal 2t and I have a finite system, imagine that now I cannot have all the values of k allowed, but I have only discrete values of k allowed. So this is going to give me these energies which corresponds to this, these allowed values of k, which I'm going to project here. Okay. And it's going to be a gapless thing. I'm going to have all the energies going up to 0 because the system is gapless in this particular case. For mu equal, for example, t in the middle, like the blue thing, I see that the lowest allowed energy is here. And when I do the quantification of k, I'm going to get energies here. But these are like the states coming from the bulk, like I said before for graphene. Besides the states which come from discretization k and projecting it in the energy thing, I'm going to get an extra state at t equals 0. So these are the bulk states which come from just getting all the intersection of my band with the allowed value of k. But then I'm going to have this extra state, which is the 0 energy state, which is not predicted by the band structure, because the band structure is going to only give me these levels here, which come from the discrete values of k, which are allowed. I'm going to have the 0 energy state, which corresponds to the state which is being localized. You remember, the state which is being localized on the two ends of the wire. The states which are corresponding to these values of the energies are the states which are being localized in the bulk. But this state at 0 energy is the state which corresponds to the end state. Okay, let me put this here to make it more visible. Okay. So the 0 energy state is the one localized. I don't have it at all. Is this state, the one here, and this state, this is the blue state, it's going to look like that. It's going to be localized in the bulk because it's coming from a bulk band. But this is an extra state which comes because the system is topological, the 0 energy state. So when do the topological states appear? Of course, the infinite thing is not going to have 0 energy state because it doesn't have boundaries. In order to have free Majoranas, in order to have topological states, you need boundaries. Because I have an infinite system, you remember the pairing between neighboring Majorana is never going to break because the system goes to infinity. So the Majoranas, the single Majoranas are never going to exist. In order to have them exist, you need to put boundaries. So if you can put boundaries by just making a wire like that. And then I have the states, two states localized on the boundaries. And there is another way that you can have Majorana is by having an infinite system, but with a domain wall. I have a non-topological region here, and I have a topological here. So if this is non-topological and this is topological, automatically at the boundary, I'm going to form a topological state. I'm going to have a Majorana state, because I cannot go between a topological and non-topological state without forming a domain wall, without forming this type of localized states. So there are two instances in which you form these bound edge states. One is in which really your system ends somewhere, or in which you have a domain wall in which, for example, here I have mu bigger than 2t, and here I have mu smaller than 2t. So this is going to be topological, this is non-topological, and the interface, I'm going to form a Majorana state. Always when I go between one topological and non-topological region, I need to form one of these edge states. Okay. So I think I'm more or less done with talking about the Kitaev model for now. I mean, I'm going to come back next week to give you more details about how do I get the wave function for this Majorana states by various methods. So I'm going to do some, for example, some matching and other things. So it's going to be more, be more detailed there. But I don't want to spend now today too much into the techniques. I'm going to talk about it next time. So now what you have to remember is that you have this simple Kitaev model. Doesn't have any spin. I didn't put any spin in it. It was just normal electrons. There are no no spin at all. It was a spinless model. But it can have free Majorana excitations on the ends on certain regime of parameters. Okay. So now this is still a mathematical model. Okay, it has physical ingredients, but we know in real life there is spin. And there are other things that we need to take into account. We never have spinless fermions in a system, and we cannot really create a Hamiltonian of this form with what we have in nature. I mean, it's too, I mean, we can try, but we have to work hard. So normally it's not possible. So now we have to try to find some physical alternative for the Kitaev model, or some physical manner in which the Kitaev model can arise in a physical system. So the Kitaev model is, again, a very simple mathematical model. But let's see what are the physical equivalents of physical equivalent models of the Kitaev, which can give you Majorana excitations in 1D. So what people some years ago, like 10, 15 years ago, thought about after Kitaev came up with his proposal was this model corresponding to quantum wires. So you have a semiconducting wire, and people said, well, what if in this wire I can add some ingredients to make it correspond to the Kitaev model? So what I can add, they said it would be some Rashba spin orbit coupling. So what is Rashba spin orbit? I had some stuff on that, but I don't remember. You may be familiar with the spin orbit coupling. You know that the spin and the orbital components can interact for an electron. But in condensed matter, this Rashba spin orbit, what actually is, in a very simple fashion, is a process in which, when I move from site I to site I plus 1, I'm flipping the spin. So it's in condensed matter, you can think about it as being some sort of a hopping term in which I'm which flips the spin. So it's like you have other types of spin orbit which correspond more to some local magnetic field. I mean, you know that you have the electric field corresponding to the whatever the atoms and everything, and that makes some sort of equivalent magnetic field, and that magnetic field can interact with the spin, and then you have the intrinsic spin orbit, which is more or less some sort of a localized magnetic field, Zeeman magnetic field. So it acts differently on the up and down electrons, but the Rashba is peculiar in that it doesn't act on the on-site, but it acts on the hopping terms. So it acts on the kinetic term, and it flips spin in the process. So this is what we usually mean when we are talking about Rashba spin orbit. In this type of problems, we are talking about hopping terms, which are spin dependent in that the spin is being flipped when I go from one side to the next. That's the Rashba spin orbit. We can have Dresselhaus also, which is also some similar thing. I'm not going to talk about it here, so you can ignore this term. It's some sort of another type of spin orbit, which is called Dresselhaus. So you see that for my semiconducting wires, I have a hopping term. This is the same one, psi j plus 1. You saw this over and over and over. Is the hopping term. I'm going between site j to site j plus 1 by the term t. But I also have now a hopping term which depends on spin, which is doing some spin flip between site j and site j plus 1. And this, it's not explicitly written here, but if you look at this thing, sigma y is telling me exactly that. Sigma y is the off-diagonal matrix in the spin space, so it means that to site j up, here corresponds to site j plus 1 down on the neighboring site. So this is the Rashba process. So in the first line, I have the on-site chemical potential. Again, I have this density type of term, psi j dagger psi j, which is a chemical potential. So I can raise or lower the chemical potential of my wire. This T comes sometimes as a convention to make things a bit more, well, I can put mu or I can put mu minus T, and you don't have to bother too much about why this T is here. Is sometimes to make the zero energy of my system in one part of the band or in the other. It doesn't really matter. It's not physically really relevant. And then I have a superconducting term, like the ingredients, the ingredients at the Kitaev were like superconductivity. So I need superconductivity of some sort. I need some electron hole type of coupling. So what people propose is that in these wires, of course, I don't have intrinsic superconductivity, but I can induce superconductivity by adding, by proximity, a superconducting substrate, which for this model doesn't have to be too complicated. It can be a regular S-wave superconductor, like whatever aluminum or whatever any normal superconductor would do. So this superconductor is added as a substrate to my wire, and this induces this type of superconducting pair. And in the electron hole space, you see this comes with the tau x, which means I'm coupling electrons with holes. I'm not coupling electrons with electrons. I'm coupling electrons with holes, like we did in the Kitaev thing. I have the C dagger terms, not the C dagger C terms. I mean, this is my superconducting terms. I don't like too much writing this Hamiltonians with too many Pauli matrices. There are people who are really keen on putting as many Pauli matrices as possible and multiplying them and stuff. But I didn't find a good formula to put on the transparency, which doesn't have everything in the Pauli matrices form. But well, people like to make it as cryptic and compact as possible. But remember, this is just a superconducting term, which is CJ dagger, CJ dagger plus CJ psi j term. And it's an on-site term. It's not like the superconductivity that we've seen in the Kitaev model, which was a pairing between neighboring sites. Here it's a simple S-wave pairing, which is on-site. It's coupling CJ dagger with CJ dagger. It doesn't couple two neighboring sites. It's just coupling on-site. It's coupling two electrons, an electron hole on the same site. So I have these three ingredients. So what does it happen when I have these three ingredients? Yes? Okay. I'll write the Hamiltonian, maybe simpler in the without. So I can write it. I have some over the side. CJ dagger. I ignore the T. I'm just putting mu. Then I'm going to get minus plus. Okay. CJ dagger. Okay, so on-site chemical potential, hopping. And actually, I can put now here, let's put alpha, which is the spin, explicitly. So now I'm summing over alpha, which is the spin. Okay. Oh, sorry. Alpha. And so J and alpha. Okay. So I'm summing over the sides, and I'm summing over alpha, which is up or down. So I have on-site, which is, of course, has the same spin. And then I have the hopping, which is the same spin. And then I have Rashba, which is alpha. And now you have to forgive me if I make a mistake, because I cannot write it by heart. But it kind of looks like that. Minus alpha. So I sum over all sides, and then I have up alpha on one side and minus alpha on the opposite side. Now, I, again, don't trust my constants, because, I have to be careful about when I put all the Pauli matrices in, but that's the principle of the thing. I have, J and J plus 1, alpha and minus alpha. So that's the Rashba, and then delta. Okay. And then, again, I have psi dagger, psi J, and then alpha and minus alpha, and the emission conjugate. Okay. So again, I have psi j, alpha and minus alpha. So that's the superconductivity. That's more or less the same thing, but written in a simpler form. I mean, without the Pauli matrices at all. I mean, if you bother about Pauli matrices, what the sigma was the Pauli matrix in the spin space, and tau was in the electron hole space, and it was doing this type of. It was describing this type of fact that you have psi dagger, and alpha and minus alpha. But this is exactly equivalent. I mean, the Hamiltonian written without the Pauli matrices. Yes. I'm getting into that now. Oh, sorry, I forgot the Zeeman term. Yeah, and then there is the last term, which is a Zeeman term, which is basically also on site, but is different for up and the down. The Zeeman term basically has higher energy for up electron and lower energy for down electrons. So this is the last ingredient which is necessary to have this model equivalent with the type. So let me show you why, because now, I mean, I just put in all the ingredients. I think it wasn't an easy proposal to make. People thought about it a lot, and then they came up with this complicated thing, which has Rajba, Zeeman, superconductivity, has a lot of things in it. But, you know, it's not clear, just looking at it, why it's equivalent to the type. So let's take all the terms now. So I have the band, you know, for my electrons, up and down. Then I add the spin orbit. So what does the spin orbit do, the Rajba spin orbit? What it does, if I look in the momentum space, it's shifting the up and the down bands laterally in K space. So I'm going to separate the up electrons and the down electrons in K space in two bands which are moved away from each other. Okay, this is the spin, this is the Rajba. This is what Rajba is going to do. I'm not going to prove it, but you have to take my word for it. If I do the analysis of the Rajba Hamiltonian, I'm going to get two bands up and down which are separated in momentum space. If I add Zeeman on top, I'm going to open a gap here at k equals 0. So I'm going to get this band and this band, which are sort of mixed between up and down spin, because you see one is coming from the up and one is coming from the down. But they are going to also have some gap. I'm going to open some gap in the middle. See if I have more stuff in here. No? Okay. I think I do. Okay. So now I have, again, these two bands and the gap introduced by the Zeeman field here. So you see that now this band is some sort of bizarre combination of the up and the down spins. And if I were to introduce some superconducting pair which would open some gap here and here, I should recover something which is similar to the Kitaev. Because what is basically Kitaev if I go back into the spin world? In the spin world, I need to separate the up electrons and the down electrons in a manner in which the superconductivity is opening the gap in one band which has only one spin, because that was what's happening in the Kitaev model. So by making this sort of bizarre combination of Rajba and Zeeman, I managed to get this band, this lower band here, which is in some sort like a good starting point to get this type of Kitaev pairing, superconducting pairing. So when I introduce superconductivity, and the chemical potential is such that I don't have any states here, so I'm inside this gap here. If I were here, then I have to open a gap here and open a gap here. If I were here, I should open gaps here and here. So this is not what is interesting, but what is interesting is to have a chemical potential which is exactly here in between this in this gap. Then the gap which is being opened by the superconducting terms is in this band. And this band, because of the spin structure of my combination of Zeeman and Rajba, will allow this type of topological type of pairing, which is going to give edge states. I know it's a bit, how should I say, is not really detailed. If you want it, I have to give you more. But in order to really go through all the details of this thing and explain you why this is like that, it will take a very long time, I think. So I'm kind of giving you some sort of intuition. It's not a full justification. But the idea is that I have the spin orbit, which is separating the up and the down. I have the Zeeman, which is opening the gap here. And I have this band, which is very peculiar because of the spin structure of this band, which is very peculiar. When I introduce a delta, then the superconductivity which arises here is topological. and similar to a spinless type of superconductivity. Okay, so now when I put the superconducting term and I take a finite size system like before, I'm taking boundaries, and if I look at the spectrum, I see again I'm going to have bands and I'm going to have some zero energy states which are being localized on the ends of the wire. So this complicated model is behaving exactly as a Kitaev model, meaning it has zero energy state, it has a bulk gap, it has zero energy states, and the states are localized on the boundaries. And the interval for which this topological states exist is the interval for which the chemical potential sits in this gap here. If I move above or below this gap, this system is no longer topological. So in order to have a topological system, I need to have my chemical potential sit in this interval, and this is what is giving me the topological phase region. So this is the simplest example of real-world material which can simulate the Kitaev model. I mean, it's again, you have to do a lot of complicated complicated combinations to make it look like the Kitaev. But at the end, I mean, if you put all these factors together, it looks like the Kitaev model. Okay. So and of course, being a real system, there have been experiments on it. So people try to look, and there have been these wires with intrinsic, with Rajba spin orbit. People knew that there are certain materials that have this type of spin orbit interactions. And they put them on superconducting substrate, and they put Zeeman on top of it. And this is the type of measurement they did. They said, oh, let's look at the conductance as a function of energy. Am I going to see a zero energy state or not? Because, like I said, in the topological systems, you are expecting some zero energy states, the topological state, and they saw some zero energy peaks. And now they said, oh, look, we have Majorana because we have zero energy peaks in these wires. With all the right ingredients, we have Majoranas. And they exist for some finite interval of magnetic field, which may correspond to the topological phase. So it kind of looks like we have Majorana. But then the other people came and said, well, they could have bound states from any other reason, like Andreev bound states or whatever other bound states, or Kondo, or there are many other possible sources of having zero energy states. And they said, well, you cannot prove these are Majoranas. I mean, you claim they're Majoranas, but you cannot prove they're Majoranas because you only see a zero energy peak. How do you know this is a Majorana or not? So this is a question which is very, how should I say, troubling in the community, because people see zero energy peaks and they say Majorana. Other people say, well, zero energy peaks don't have to be Majorana; they could be something else. And there are always, controversies. And in this other thing, they look now at the, like I said, you can look at the position and the energy, and to look at the spectrum, and they saw that there are some states which are zero energy and they are localized on the end of the wire. That's a bit better than having a zero energy peak, because you already know that your state is localized on the end and not some stray state which can live in the middle of the wire. These are actually not even semiconducting wires. They're a bit more complicated systems made of magnetic atoms, magnetic chains of atoms. So they could see some state which was localized on the end, which was zero energy. They said, oh, this is a Majorana. But again, you cannot have other type of states which make, other type of processes which make zero energy states on the end of the wire. So I don't know. Who knows? For now, there is still no definite proof that this is a Majorana. So there isn't for now any. There are some proposals about actual braiding of the states, because they should be non-abelian. So if you could show that the states are non-abelian when you braid them, that could be some sort of, not proof, but better indication. If I have time in the second course, I'm going to propose some tool. I mean, I'm going to describe you some tool which we proposed that was, definite. In an ideal world, that would be a measurement that you could do, and that would tell you if it's a Majorana or not. But for now, I don't have a proposition of how to measure it. It's still a mathematical tool, and if we manage to find a way to measure it, that could be a some definite proof, but there is no definite, there is no definite prediction of how can you say it's a Majorana or not. I mean, 100% sure. Okay. So this is about key-type model in 1D. So now for the rest of the time, I'm going to go through more, without getting into details of Hamiltonians and solving and everything. I'm just going to give you more examples of other topological systems which exhibit Majorana or other type of topological states. So I'm going to, it will be more like pictures and pictures and words than actual calculations. So I talked about the Kitaev 1D model, and this had end states at the end of the wire. But you can also have, like in graphene, you could have edge states, meaning you could have a 2D system, and this 2D system could have 1D edge states. So I imagine I have like here a square lattice, and then I have some ingredients to my Hamiltonian, which would make it possible to have Majorana edge states. So what are the propositions for to form Majorana in 2D? So first one is simple. I mean, I just take the Kitaev model in 1D and I make it 2D. Nothing stops me from doing that. I have the hopping, stays the same. I have the chemical potential, stays the same. And I have superconductivity, stays the same. It's just now instead of being able to hop only along one direction, then I can have a hopping in the other direction as well. So if I write that type of Hamiltonian, the equivalent of the spinless 1D Kitaev in 2D, then indeed I can get Majorana edge state. Let's see if I had more details here. No, sorry. Okay, so now if you remember the picture that I gave for graphene, in graphene I had some bulk states. Well, it's not these ones, but I had some bulk states, and then I had the band at zero energy, the band of edge states, which was appearing extra, the band of zero energy states. If I'm looking at a model like the spinless Kitaev, something similar is going to happen. I'm going to have some bulk modes, which are going to come from projecting my bulk band structure in one direction, along this direction. So again, I'm going to have quantification of modes along this direction. I'm only going to have some allowed values of k, which is going to give me the quantification of the bands. And I'm going to have a free k, like a good momentum, good wave vector, which is going to be along this direction, and is going to be this k. And I'm projecting now all my bands along this direction, so I get these quantized modes. And these are going to be the bulk. This is going to be the bulk. But on top, I'm going to get these bands like that, which are not there in the bulk band structure. So it's the same phenomenon which appears for graphene. I have an extra band which corresponds to the edge. It's the same phenomenon which appears in 1D, where I have one state which appears, which is not there in the bulk, which is at zero energy. And here, for this case, I'm going to have this type of crossing states, meaning one of these states has a dispersion like that, and the lower one has a dispersion like that in energy. They are called like, I think chiral, sometimes chiral, sometimes helical. There is some sort of people, okay, not always with the same words for chiral and helical, so I'm not going to give you all possible interpretations of those words, but the idea is that these states are propagating with some dispersion which is of this form. E of k is v times k, and E of k is minus v times k. And you have propagating Majorana states on the two ends of the wire, and you see that at k equals 0, they have zero energy. So they are the zero energy states we are looking for. But you also have other states at different k which are not at zero energy, and now you don't really have a Majorana state, you have some sort of a Majorana band which is crossing 0 at k equals 0. So these are going to be like the propagating Majorana states on the ends, on the edges of a system. Yeah, sorry? I'm getting there. This was like just the spinless. This is like a theoretical thing for the spinless. I'll just say it in a second. So this is mathematical, of course. No physical model being described exactly by the spinless Kitaev. What you could imagine is to make the proposal for the 1D wire also in 2D. Imagine I have a two-dimensional system. I have Rajba. I have Zeeman. I have superconductivity, which is being induced by a substrate. So if I were to have a 2D structure with these ingredients, I can write down the same type of Hamiltonians as for the 1D wire, and I'm going to show that it can actually exhibit Majorana. So a square lattice with Rajba, Zeeman, and superconductivity is going to exhibit Majorana. Now it's a bit harder to get materials that have these properties. They have strong Rajba for 2D, but well, it's a proposal. It's not so simple as in 1D where you have the wires and everything is working smoothly. There are like, we are also thinking about graphene, but graphene doesn't have Rajba. Actually, superconductivity is not so bad because you can induce it by a substrate. But graphene doesn't have intrinsic spin orbit. So if you were to have graphene with spin orbit, which is not the case at this moment in real graphene, but if you were to have some graphene which had some Rajba spin orbit, then you could get Majorana states. But you don't for now, but it's a proposal. I mean, you could think about like cold atoms, hexagonal lattices, where you could maybe make up some, I don't know, you can think about many things, but you know, the idea is that in a hexagonal lattice, if you were to have Rajba and Zeeman and superconductivity, you could also get Majoranas. And Rajba doesn't have to be always Rajba. You can also have an inhomogeneous magnetic field which could play the same role. So imagine instead of having this type of hopping, I can imagine another ingredient which actually works very well. I mean, we did a calculation. So imagine that you have a term but then I have a V. Okay. So I have a Zeeman term, but this is dependent on the position. The Zeeman term depends on the position. So I imagine I have, for example, a cosinusoidal or sinusoidal dependence of the Zeeman field with position, or I can even have a rotating field, meaning it's changing orientation, not only value, as I go, you know, as I move along the wire, as I move into D. So I can have if I have an inhomogeneous V, this actually works very similarly to Rajba, and it can generate Majorana. So this is one ingredient which people have played with, to have inhomogeneous magnetic fields in a 2D system which can make Majorana states. So this is an example here for graphene with these ingredients. You can see the formation of edge states, and differently than what I told you at first, that if you had graphene and non-topological states, they would be destroyed by the disorder on the edges. So here you see that they are still there. Even if I'm perturbing my edges, they will be still there because these are topological. These are not the edge states which come just from the structure of graphene. They come from these ingredients and they are topological, and they are not being destroyed by perturbing the edge or by adding disorder in the bulk or by any other things. They stay. So they are like topological states. Okay. So this was about Majorana. But Majorana states are not the only topological states that we study. And Thierry is going to talk Thierry is going to talk about another topological system, which is the quantum Hall effect. So he's going to spend like 4 lectures describing how do you get edge states and, you know, all sorts of funny physics in the quantum Hall effect. So Majoranas are one example. Quantum Hall effect is another example. But you also have what is called topological insulators. So I'm not a big specialist in topological insulators, so that's why I'm not really getting into the details of what is a topological insulator. The idea is that these are insulators in the bulk. So if I were to have an infinite system, it's insulating. It has a gap. But I form edge states which are conducting. So my bulk system is insulating. I have a gap. But if I take a finite size system, this finite size system is going to be conducting because it has edge states. It's like in the quantum world. I have some edge states, and these edge states are conducting, but the bulk is not conducting. The bulk is insulating. So the simplest example comes from the type, maybe not the simplest, but the one I found the simplest is coming from the Kane-Mellon model. So I'm going to write it down a bit. So this is based on the hexagonal. Lattice, like same as graphene. But besides the hopping term, which again is coupling, nearest neighbors. I mean, here the notation is a bit different because I'm using C for both A's and B's, but I mean, you understand. I mean, when I'm talking about nearest neighbor coupling, I'm just going between A's and B's. I have a higher order hopping, which goes between one atom and the, this is the second atom. Okay. I have 6. I'm going between one atom and the 6th next to nearest neighbors. So this one has 3 nearest neighbors, and you have and then I have 6 next to nearest neighbors. So the electron can hop with a regular type of hopping to the nearest neighbors, but it can hop to the higher order, next to nearest neighbors, to the higher order neighbors, with some spin orbit, with some hopping amplitude which depends on the spin. So if I were to hop a spin up or a spin down, the hopping amplitude would be different. So it's not like Rajba, because remember, Rajba, I was hopping between 2 neighbors and I was flipping spin while I was hopping. This type of hopping, I'm hopping between this and this, but I'm not flipping spin, but the hopping is spin dependent. So I'm going to have, okay, like that, C up I plus 2, okay. So I'm hopping between side I say I plus 2 is not really I plus 2, is the next nearest one, but then this has a alpha up, but I have an alpha down. I have, when I'm hopping a down electron, it's a different amplitude than when I'm hopping an up electron. So alpha up is not the same as alpha down. So I'm having different amplitudes for hopping for up electron and down electrons. So I'm hopping to the next nearest neighbor, but with an amplitude which is dependent on spin. So that's the term, the spin orbit type of term, which was introduced by Kane and Melle to show that you can form a topological insulator based on this hexagonal lattice with this type of hopping processes. Again, for the 100th time today, I had the bulk bands, which were showing a gap, and I have the edge states, which were forming inside the gap, and they're propagating along the edges. Okay, here actually, they're propagating along the edges. But what's interesting about this model is that in this band, I mean, I color coded it. So the blue is a state which is propagating along the left border, and it has a spin down. The green is propagating along the right border and has a spin up, but these two have the same dispersion. And then you have the opposite dispersion. You have, I think this is violet, this is not blue. You have the violet, which has a spin down, it has a spin up, which is propagating along this, and you have a red, which is propagating on the right and has a spin down. So you have spin up and spin down, which are separate in space, and also they are separate in dispersion. So you have double mode on the edges. So you have an up and a down together propagating oppositely along the same edge, and it's exactly opposite on the opposite edge. So you have 2 opposite spin modes propagating together with opposite dispersions on the two edges. So it's a quite funny. It's a quite funny system, which gets like these edge states, which are also polarized in spin. So then you can imagine you have a lot of spin physics, which can come on top of this, because you have these spin polarized edge modes. You can write down you can think of a lot of problems of, I don't know, whatever you can think of. But it's a very interesting system because it has these spin polarized edge modes which propagate oppositely on the edges. Okay, so this again, there is no superconductivity here. I have no Majoranas, But I have a bulk system which is insulating, and I have these propagating modes which are conducting and which are spin polarized, and this makes my system not an insulator but a conductor, and it's actually topological. It's what we call the topological insulator, because again these states are stable. They don't depend on parameters. They are stable with disorder. They are stable with the parameters of the system. So we call this a topological insulator. Okay. So as I said, another example of topological system is quantum Hall, and Thierry is going to talk about that. And there are only two more examples I'm going to talk about, and then I'm going to stop. I mean, again, I'm not entering much into the details. One is very peculiar, which we call the Weil semi-metal, and is funny because this is a 3D thing. This is so complicated, I'm not going to give you a Hamiltonian because it has a very complicated type of hopping with a lot of magnetic flux and other things. I mean, you can, well, you can look at it. It has a lot of terms in there. You have to try to understand all of them, but the physics is not really coming from there, the interesting physics, even if, of course, you need it as a basis to make it work. But what is interesting about this is if you write down this complicated Hamiltonian, what's going to happen, you're going to have some dispersion, some energy for the bulk system, not for the, okay. You're going to have, I'm going to now talk about Kx, Ky, and Kz. I mean, these are like the momentum. Now, since I'm in 3D, it's a bit more complicated to draw a band structure because I need 3 Ks, and well, I need a fourth to do the energy. So it's a bit complicated, so it's a bit schematic. You cannot draw in for dimensions. But what happens is that if you look in the Kx, Ky, Kz space, you're going to see that there are 2 points, special points, for which you have a gap, which are gapless. It's like in graphene, you had the corners of the Brillouin zone, which were gapless. You had some Dirac dispersion close to those points. For Weil, you have 2 points. And close to those 2 points, the band structure is gapless. Everywhere else, there is a gap. But for these 2 points, the special points, the band structure is gapless. Same as if you remember in graphene, we had everything was gapped except for the corners of the Brillouin zone, which were gapless. We had some cones, Dirac cones. Here we have some sort of Dirac cones as well, but they are in 3D because I have Kx, Ky, and Kz. So I have some sort of 3D Dirac cones. I have a zero energy closing the gap at these 2 points, and they are called Weil. I mean, they are like Dirac-like points, but they are called Weil. And the electrons have linear dispersion along this, close to these points. So what's interesting about this system is that not only it has these points, but also it has some bizarre surface states. So now we cannot talk here about edge states because this is a 3D thing. So now imagine the 2D band structure then was projecting into 1D edge states. So I have a 3D band structure, so I'm projecting into surface states because then that's my boundary. Okay? So if I have a 3D system, I need to have topological surface states. I mean, to first step, I have topological surface states. So what happens to this? What happens to this system is that it has interesting surface states. And if you remember how we were obtaining the edge states for the regular systems, for the 2D systems, I had a bulk. I had a bulk band structure, and then one momentum was being quantized, and then I was left with 1. And then when I was projecting the band structure along that, then I was getting some sort of edge state, which I had the bulk mode, and then I had 1 edge mode. So here, what happens is a bit more complicated because I'm in 3D, but it's kind of it's a bit similar. Now I no longer have one allowed k momentum because when I'm quantizing one direction, I'm being left with two allowed directions. So I have kx and ky which are allowed. Okay. So I'm going to have now some sort of surface states, not edge states, which are going to have some dispersion, which is very bizarre. But oh, sorry. Okay, let's lift this up a bit. I'm going to have some allowed range. Here I had one point in 1D. I had one point around which I could have like a crossing like that of zero energy states. In this 3D thing, I don't have one point, but I have an arc. And this is called the Fermi Arc. Okay. And then I have, around this Fermi Arc, I have this type of states. Okay. But the states are, the surface states are going to zero at this point in this 2D surface, which is the equivalent of the point in 1D. Now in 2D I have an arc, and along this arc I have this state which intersects zero on these special points of the Fermi Arc. And this is like, well, quite cool physics. I mean, it's hard to grasp it starting from the actual Hamiltonian of the 3D systems. The 3D system, you kind of have to do a lot of numerical stuff to get it to work, or some other type of analysis. It's really hard to get the intuition out of it, except that, well, you have the projection of the two Fermi points, two Weil points, which are going to be these two, and then in between you have an arc, and along this arc you have some sort of dispersing surface states, not edge states. So this is a bit tricky, but if you are going to this course, have some idea what somebody is asking me what is a Weil semi-method, just to have some idea what it is, even if I don't really want to get into the details because it's quite complicated. But the idea that you have a 3D system with two Weil points where the energy dispersion is going to zero, and then if you look at the surface states, equivalent to the fact that you had Majorana or other topological states which are crossing at one point in K, here the surface states, they cross at an arc in the Kx, Ky, and you have dispersing states along this arc. Okay, that's the Weil semi-method. And the last one, which is very simple, but not so simple to work with, is what we call the higher order topological insulators, in which the edge states don't necessarily have dimensions you'd expect. So what you'd expect, if I have a 1D, then I have 2 points. Those are my, the edge states for the 1D system. If I have a 2D, then I have lines, edge lines. If I have a 3D, then I expect surface states. And we see that the dimension of the edge state is 1 less than the dimension of the system. So if I have a 1D system, then I have a 0D state. If I have a 2D, then I have a 1D state. If I have a 3D system, I have a 2D state. I mean, that's the first order topological insulator type of thing. The dimension of the edge is 1 less than the dimension of the bulk. But there are systems in which the dimension of the edge is more than 1 less than the dimension of the bulk. So if I have a 2D system, you can imagine I have points, which are topological states. So dimension of the system is 2, dimension of the edge is 0, so the difference is 2. So these are called like second order topological insulator. If I have a 3D system, I can have edge lines, which are topological. So again, dimension of the system is 3, dimension of the edge is 1, the difference is 2. So these are examples of order 2 topological insulator. And then you have extreme cases when you have a 3D system and the dimension of the edge is 1, is 3 here, it should have been 3. Dimension of the edge is 0, so the difference between the bulk and the edge is 3. So this is a third order topological insulator. And for each of them, there are models, and you can get into more complicated analysis of how to get them, how to analyze them. Okay, I'm not going to get into that. I just wanted to let you know that these things exist, that you can have higher order topological insulators, which are characterized by this type of properties. Experimentally, I am not a specialist, so I don't know. I know that there are models and probably there are proposals, but I'm not sure they actually been they've been verified 100%. I don't know that. Yeah. Okay, so I think I can stop here for today, and if you have questions, feel free. I mean, I'm. Thank you.